So let's move on to the second chapter of our course on Introduction to Climate Science. This is about data, very broadly data, and we'll look at a range of data. So we showed the temperature, pressure, precipitation, and so on at Corvallis, and then we showed state level temperatures for Oregon, US level, global level temperatures, and we talk about global warming all the time, and you probably know that it's some sort of an averaged temperature. So how do we get all this data? You probably already know that temperature is measured with thermometers. It's just a question of how they are installed, where they are installed, what is the network, and how do you measure temperature up in the atmosphere. How do satellites measure temperature? There are buoys in the ocean that go up and down and measure temperatures. There are buoys in the ocean that are anchored to the bottom and measure temperatures on a rope. There are gliders. There are ships that are going across and measuring temperature. So that's just temperature. Then you think about all the other variables in the atmosphere. You want to see clouds, gases, dust, humidity, what else? All sorts of things, right? Radiation. And in the ocean you want salinity, chlorophyll, land chlorophyll, ocean chlorophyll. Anything and everything you can measure is useful, right? So let's start with this. This is showing global average surface temperature change from 1880 to 2018. We already talked about this a little bit. Anomalies from the 20th century average are shown. So the 20th century average is subtracted from data at each year. Let's say this is the annual mean temperature we are looking at. So you take average of each year, like 1880, and you subtract the 20th century average from it. You can use any baseline. It just changes the relative amounts a little bit, but the story remains the same. So we are saying the temperatures till about the 1930s, as we saw before, were below the 20th century average with year-to-year variability, decade-to-decade variability, and then they vacillated around the 20th century average temperature, and then they have been above it with year-to-year temperatures. We already mentioned a little bit about where the year-to-year temperature changes come from. As we said, ocean can store the energy and it can release the energy, for example, during an El Nino or a La Nina, which we will learn a little bit more about later. And once we have this kind of a data, this is global land and ocean mean. So you have to imagine that we have taken all the data we can get and averaged them. And the data is obviously not the same amount or same locations over the whole period, because if you go back to the 1880s, temperature data were being collected, but as you can imagine, probably far fewer in the ocean than on land. And now, since we became aware of global warming, and we started making weather predictions, climate predictions before becoming aware of global warming, we started to collect more and more data with various platforms like the balloons, satellites, autonomous weather stations, crowdsourcing of data now as well, WeatherBug and other things, and so on and so forth. So the distribution of data and in space and time is not uniform. So those things do matter for reconstructing this, and we will see an example of how different reconstructions of temperature give slightly different estimates of the trends, which we are talking about here, which we talked about before as well. Errors due to unequal sampling have been estimated, so maybe I should read the whole thing here. There are a few other groups around the world who calculate global average surface temperatures. For example, NASA, the NASA GISS, Goddard Institute for Space Science, Climate Research Unit of the East Anglia University, Berkeley Earth's surface temperatures, and so on. Errors due to unequal sampling have been estimated to be about 0.2 degrees centigrade during the early part of the record and decreased to 0.1 degrees C during the more recent part. So the errors themselves have been reduced. This is a key figure. The linear trend over the full period is 0.08 degrees centigrade per decade, and that over the last 100 years is 0.10 degrees centigrade per decade. And that over the last 50 years is 0.18 degrees centigrade. So global warming, or at least the warming that we are recording over this time period, is positive. So temperatures on the average across the globe are increasing, and the rate of increase is increasing. So there is accelerated warming as we go forward in time. If you look at the last 50 years of change, you can see that the warming is not uniform. So when you average like this and you talk about global warming, obviously we have to be careful, especially because land warming and ocean warming are different. Tropical warming and high latitude warmings are different. Northern high latitudes and southern high latitudes are different, and so on. Why? We will see as we go forward, but you can imagine that because there are winds that are moving the heat around, there are places where more greenhouse gases are being emitted, and some greenhouse gases are quickly moved around and mixed across the globe. Some are not, some remain local. Pollution can be very local. And there are other reasons why there is actually no warming, or maybe even a slight bit of cooling over this particular region, as we will see. This is the so-called Greenland, Iceland, Norwegian Sea, or the North Atlantic, where specific processes happen which allow the heat to be taken away into the deep ocean, as we will see. And there is a accelerated or a larger warming here in the polar latitudes in the north compared to the south and elsewhere. And land warming is more than the ocean, as you can imagine, because land has higher heat capacity than the ocean. So the dynamics, the circulation, the uneven distribution of pollution and greenhouse gases, and other processes like what determines the energy balance. So as energy is coming from the sun and is going back out to space, and we'll see how the energy coming in and the energy going out are different, and why that energy balance is different here than here. We already mentioned a little bit that because it's a sphere, more of the sun's energy per unit area is received at low latitudes, and the curvature makes the area larger, so per unit area less of sun's energy is received at higher latitudes, and then you add the tilt and the seasonality and so on. And we mentioned that we end up with net surplus of energy in the lower latitudes, net loss of energy at higher latitudes, plus that net loss of energy is going to create snow and ice, which, as you can intuitively imagine, can reflect more of the sunlight, which means they are receiving even less energy. If you start global warming, then if ice and snow begin to melt, then that reflectivity reduces, so you can keep more energy, and you can also create water vapor change because of this Clausius-Clapeyron we talked about, and the cloud changes because of that. And so those kinds of processes begin to give you non-uniform warming with what is called polar amplification. We'll come back to that in the second part of the course when we look at climate change, but just keep this word in mind, polar amplification, and keep this map in mind that the warming is not uniform and there are regions where actually cooling happens. So when we look at global warming like this, the data that is distributed here allows us to derive these contrasts, and then when we average, we look for the kind of errors that are there in the data, or a lack of coverage gives us certain errors as well. So I'm adding science together with data. This chapter is on data, but this gives you a sense of how important it is to have not only data, but data for long periods of time to do these kinds of things, and data sampling over the globe, including the ocean and the cold places towards the poles, to get a good sense of how the warming is happening. Okay, the patterns of warming. Okay, these are critical. So I will stop this podcast here, and we will look at other details of the data as we go forward in this chapter. Okay.